Question 2. Nitrogen and hydrogen were mixed in a 1 to 3 mole ratio, so there's 1 mole of nitrogen for every 3 moles of hydrogen, and left to reach equilibrium. When equilibrium was reached, the total pressure in the flask was 150 kilopascals, so all the gases contribute towards 150, make a pressure of 150 kilopascals, and they're all contributing. The mole fraction of NH3 in the mixture is 0.8. So that means the other two gases, the nitrogen and the hydrogen, must be making a mole fraction of 0.2. So the mole fraction of the NH3 is 0.8, so by subtraction, the remaining gases, the N2 and the H2, must make a mole fraction of 0.2, the remaining part of the fraction, so that 0.8 and 0.2 adds up to 1. We know that 1 out of 1 to 3, or 1 out of 4, a quarter is nitrogen, and 3 out of the 4 are hydrogen, because the ratio is 1 to 3. So the mole fraction of the nitrogen there is a quarter of the remaining 0.2, and the mole fraction of the hydrogen is 3/4 of the remaining 0.2. So I've multiplied that out, and therefore the partial pressure of the nitrogen is its mole fraction 0.05 multiplied by the total pressure 150, that's 7.5 kilopascals. The partial pressure of the hydrogen is its mole fraction 0.15 times the total pressure 150 kilopascals, which is 22.5, and the partial pressure of the ammonia is 0.8 multiplied by the total pressure 150, 120 kilopascals. Give an expression for the equilibrium constant Kp. So it's the partial pressure of the ammonia, which is on the right hand side, squared, divided by the partial pressure of the nitrogen, divided by the partial pressure of hydrogen to the power 3. So it's very similar to a Kc, an equilibrium constant, but instead of using concentrations, using partial pressures, because a partial pressure is effectively the concentration when you're talking about gases in a system. In a different equilibrium mixture under different conditions, the partial pressure is shown below. Calculate the value of the equilibrium constant Kp. So I'm just putting these numbers in really. So I've worked out my Kp here, and I'm just putting the partial pressure of the ammonia squared divided by the partial pressure of the nitrogen, and that divided by the partial pressure of the hydrogen to the power 3. So I'm just putting those numbers in, and when you put those numbers in and calculate it, it comes out as 0.0029. They allow anywhere between 0.0029 and 0.0030. Calculate the units. Well, on the top I've got kilopascals multiplied by kilopascals, and on the bottom I've got kilopascals multiplied by kilopascals multiplied by kilopascals, 3 of them, and another kilopascals on the bottom. So I've got 2 kilopascals on the top, 1, 2, 3 kilopascals on the bottom, and another one, a fourth one. So 2 of those cancel, so I've got 1 on the top and kilopascals on the bottom. That's kilopascals squared, 1 divided by kilopascals square, or you could say kilopascals to the minus 2. The enthalpy change for the reaction is minus 92. So going in the forward direction here, so when nitrogen and hydrogen make ammonia, then it's minus 92. Minus 92 is an exothermic reaction, so when the nitrogen and hydrogen make ammonia, it gives out 92 kilojoules per mole. It's exothermic. So if I increase the temperature by Le Chatelier's principle, the reaction will try and lower the temperature of the system. So if I increase the temperature by Le Chatelier's principle, it will oppose that and try and lower the temperature. So it's not going to go to the right hand side, because going to the right hand side it's exothermic and gives out heat to the system. It's going to go to the left hand side. So it's going to decrease. If it goes to the left hand side, then these values on the top, the ammonia decreases because you're making less and less ammonia. You're making more and more nitrogen and hydrogen if it's shifting to the left hand side to try and lower the temperature. So you're making more nitrogen and hydrogen and less ammonia. So if you're making less ammonia and more nitrogen and hydrogen, the numbers on the bottom are going up and the number on the top is going down. So the Kp decreases, and the way to explain that is the reaction is exothermic, gives out heat in the forward direction. Increasing the temperature by Le Chatelier's principle, it's going to try and oppose that change and lower the temperature, and it can do that by shifting the position of equilibrium, it should say, shifting the position of the equilibrium to the left hand side. because going to the left hand side it's endothermic and takes in heat.